I wanted to finish the two problems that we started today in class. This first problem where we're solving this polynomial equation, or we're finding the zeros of the polynomial function, means the same thing. We had graphed this and we had seen that the graph of this polynomial touches at x equals 1. That means that its multiplicity is even. If it touches the x-axis at a particular 0, its multiplicity of that factor is 0. So the multiplicity is even, so the factor x minus 1 is repeated an even number of times. So this means that this polynomial either factors to x minus 1 times x minus 1 times a quadratic, and it would be quadratic because the two first degree factors would give us a degree of 2, and multiplying that by something would also have to be degree 2 to give us a polynomial that's degree 4. Or it factors to x minus 1 to the 4th power. It has to be one or the other. Well, it's not going to be this one, not this one, no. And it's not going to be that one, because if I multiplied that all out, x minus 1 times x minus 1 times x minus 1 times x minus 1, the constant factor at the end would be 1, because I'd have that last being 1 and 1 and 1 and 1. Well, it's not, it's 13. So it doesn't factor to x minus 1 to the 4th. It factors to x minus 1 times x minus 1 times some quadratic factor. So we can figure out what this quadratic factor is by dividing this polynomial by x minus 1 twice. And I'm going to do that using synthetic division. So I write the coefficients of my dividend. Bring the 1 straight down. 1 times 1 is 1. Write that. Oops, we had an issue. Write that in the second column. Negative 6 plus 1 is negative 5. Negative 1 times 5 is negative 5. Write that in the third column. Add 22 and negative 5, that is 17. 17 times 1 is 17. Write that in the fourth column. Negative 30 plus 17 is negative 13. Negative 13 times 1 is 13. The remainder is 0, which is exactly what I expected. I know x minus 1 is a factor. So if I divide this polynomial by x minus 1, I have to get a remainder of 0. And let's do this a second time. Let's divide it by x minus 1 again. Bring the 1 straight down. 1 times 1 is 1. Write that in the second column. Negative 5 plus 1 is negative 4. Negative 4 plus 1 is negative 4. Write that in the third column. 17 minus 4 is 13. 13 times 1 is 13. Write that in the fourth column. Negative 13 plus 13 is 0. And that's exactly what I expected to happen. And what I have down here are the coefficients on the quadratic factor. So this is going to be x squared minus 4x plus 13. So far, this thing factors to x minus 1 times x minus 1 times x squared minus 4x plus 13 equals 0. And I know that quadratic is not factorable. It's not factorable because I would need two factors of 13 that add to negative 4. There are no two factors of 13 that add to negative 4. So I'm going to use the quadratic formula on that part. So I'm going to take this quadratic factor and I'm going to use the quadratic formula to find the solutions to that. Okay, so we have x squared minus 4x plus 13 equals 0. A is 1, B is -4, and C is 13. A, B, and C are constants. They are numbers. They do not include any variables. So don't try to plug in variables into this formula. This formula, you're only going to plug in constants. All right. So let's do the plugging in. I have a -4 is going to give me +4. Plus or minus the square root of -4 squared is 16. I always square that to make sure that I get the sign to be positive. -4 times A is 1 times C is 13 over 2 times 1. So I get x is 4 plus or minus the square root. And I'm going to take out my calculator and do this. Is 16 minus 52. Actually, I think I can probably do that in my head. 16 minus 52 is -36. And it doesn't surprise me. I'm going to get complex conjugate solutions here because I saw that the graph touched at 1, but I know this thing didn't factor to x minus 1 to the 4th power. So since it's only touching at 1 and it's not crossing anywhere else, then I assume the other two factors are going to be complex. Okay, let's go ahead and simplify this. The square root of -36 is 6i. I can factor a 2 from the numerator and cancel that with the 2 in the denominator. So my two complex factors are 2 minus 3i and 2 plus 3i. And they are complex conjugates of each other because the only difference in the two numbers is the sign of the imaginary part. So what are my solutions to this? Well, 1, 2 minus 3i, and 2 plus 3i. And the 1 is repeated twice, but I don't need to write it twice. All right, so here is the fundamental theorem of algebra. If f of x is a polynomial of degree n, where n is greater than or equal to 1, then the equation f of x equals 0 has at least one complex root. So what this means is every equation has a solution. They may be complex. As a matter of fact, every polynomial equation degree 1 or greater has the number of solutions equal to its degree. So if it's linear, it has one solution. If it's quadratic, it has 2. If it's a third degree polynomial, it has 3. Some of those solutions may repeat and some of them may be complex, but every polynomial equation has a solution. Okay, the linear factorization theorem says that every polynomial function can be factored to a constant times a series of linear factors. So let me read this. If f of x equals a sub n x to the n plus a sub n minus 1 to the x times x to the n minus 1 plus etc., where n is greater than or equal to 1 and a sub n can't be 0, then this function will factor to a constant a sub n times a series of linear factors, where the constants C1, C2, and C3 are complex numbers. And C1, C2, C3 can be complex numbers in the form where the imaginary part's 0, so they're just real numbers, or in the form where the real part's 0 and they're just imaginary numbers. But C1, C2, C3, etc., these are complex numbers in the form a plus bi, where a or b could be the number 0. All right, so we're going to use this to find the function that fits these parameters. Find a third degree polynomial function f of x with real coefficients such that -3 and I are zeros, and such that f at 1, f evaluated at 1 is equal to 8. All right, so if this is a third degree polynomial function, then it is going to have the form f of x equals a sub n x minus c1 times x minus c2 times x minus c3. Since it's a third degree polynomial function, it will have 3 zeros that are complex. Now, the problem tells me what 2 of the zeros are. It tells me one of the zeros is -3. So let's call that C1. And it tells me another zero is I. But what's the third zero? Well, if I is a zero of this polynomial function, then its conjugate must be. If you have a complex number solution, a zero of a polynomial function, its conjugate must also be a zero, a solution. So if I is a solution, negative I has to be, because that is the conjugate of I. Okay, so this thing factors to f of x equals a sub n times x minus a minus 3 times x minus I times x minus a minus I. So let's rewrite this. A sub n times x plus 3 times x minus I times x plus I. And I'm going to go ahead and multiply this all out. I don't know what a sub n is, but I can figure it out from this right here. F of 1 is 8, excuse me. I can plug in x equals 1 here in this equation, and f of x equals 8. And I can figure out what a sub n is, but I'm going to go ahead and multiply it out first, and then we'll do that. Okay, so I'm going to multiply the polynomials together. And I'm going to first multiply these two together, because I happen to know what happens when I multiply a complex number by its conjugate. I happen to know that I'm going to, oh, come on, there we go. I know you like me hearing me go, while I'm doing this. What happens when I FOIL this, that outside and inside add to 0, and then I end up with minus I squared, but minus I squared is plus 1. I squared is -1. So if I have minus a minus 1, I get plus 1. So that multiplies to x squared plus 1. Then I'm going to go ahead and FOIL the x plus 3 times x squared plus 1. That's going to be x to the third plus 3x squared plus x plus 3. And so now I can determine what a sub n is by knowing f of 1 equals 8. So I'm going to make that substitution. 8 equals a sub n times 1 cubed plus 3 times 1 squared plus 1 plus 3. And that's going to be a sub n times 1 plus 3 plus 1 plus 3, which I believe is 8. So a sub n is 1. So my function is f of x is equal to 1 times x to the third plus 3x squared plus x plus 3. So that is the third degree polynomial function that has a 0 at -3 and at I and at -I. And the evaluation of the function when x is 1, y is equal to 8. All right, Descartes' rule of signs. So Descartes is that guy, Rene Descartes, who said, I think, therefore I am. He was a French mathematician and philosopher. And he's the one that came up with the coordinate plane. We told that story early in the semester. But this thing that he came up here is absolutely brilliant. So what Descartes says is, if you look at a function, a polynomial function, and you count the number of times that the terms change sign from positive to negative or negative to positive, you can determine the number of positive real zeros that polynomial function has. Then he says, okay, if you take that same function and you evaluate it at negative x, and you count the number of sign changes in that function from positive to negative or negative to positive, that is the number of negative zeros that function has. Okay, let's see if it works. So let's determine the possible number of positive and negative real zeros of f of x equals x to the fourth minus 14x to the third plus 71x squared minus 154x plus 120. So the first thing we're going to do is we're going to count the number of sign changes in the function. Okay, so we're going from positive to negative. There's 1. We're going from negative to positive. There's 2. We're going from positive to negative. There's 3. Negative to positive. There's 4. So Descartes says, since there are 4 sign changes, I could have 4 positive real zeros. Or they could be 4 imaginary zeros. I mean, that's the way this works. It could be 4 imaginary. So he says, okay, then subtract 2. So there could be 2 positive real zeros, and 2 imaginary. And then he says subtract 2. So there could be no positive real zeros. And there could be 4 imaginary. So based on the number of sign changes of this function, you could have 4 positive real zeros. They could all be positive and they could all be real. Or there could be 2 positive real zeros and the other 2, maybe they're negative, maybe they're imaginary, I don't know, but they're not positive. Or I could have no positive real zeros and they could all be negative. Well, I'm going to check that out in just a second, by the way. Or they could all be 4 imaginary. They could all be 4 imaginary zeros. So he says, okay, evaluate this function at negative x, and that will help us with the negative if any of these are negative. Now I'm going to give you my quick and easy way to evaluate a polynomial function at a negative x. If the degree of your term is even, you leave the term alone. If it is odd, you change the sign. So there are no sign changes. So there are no negative real zeros. So this is the case where either we have 4 positive real zeros, or we have 2 positive real zeros and the other 2 are imaginary, complex, or we have no real zeros and all 4 of them are complex or imaginary. Okay, so I can check this out by graphing it. So I'm on my iPad here, so I don't really have a very good calculator, but I'm going to go open my calculator anyway. And I am going to graph this. Let me clear out what I've graphed before. So I'm going to graph this particular function. So I have x to the fourth minus 14 x to the third plus 71x squared minus 154x plus 120. Okay, I'm going to graph this. And I'm going to use my fingers to kind of expand this a little bit. And it's kind of hard to see, especially with me trying to, here we go. Since on my iPad, it's kind of interesting. If you graph this on your calculator, you'll see what it's doing much easier. Oh, that's not too bad. Oh, squishing it up. There we go. There we go. Okay, what happened? There are 4 positive real zeros. This polynomial function is crossing the x-axis at 2, it's crossing at 3, it's crossing at 4, and it's crossing at 5. So Descartes said that there is a possibility that this polynomial function could have 4 real zeros, and it does. So Descartes was correct by just looking at the function and seeing that it had 4 sign changes. We could determine that there could be, anyway, 4 positive real zeros, and in actuality, there are. And that is the end of this section. So I'm going to stop the recording now and post this, and hopefully that'll help you a little bit.